Pop quiz. For the reaction nitrogen plus hydrogen forming ammonia, if we crank up total pressure while keeping the composition the same, which way does the balance tip? Left, right, or no change? Lock your choice now. We'll reveal and explain it shortly. In this video, you'll learn how pressure affects Gibbs free energy, why we use the equation delta G equals delta G naught plus RT times the natural log of Q, and how to compute delta G under non-standard conditions. Start with the big idea. For ideal gases, a species' free energy rises with pressure. G equals G naught plus RT times natural log of pressure. For a whole reaction, that stacks into delta G equals delta G naught plus RT times natural log of Q, where Q is the reaction quotient built from partial pressures. Why does pressure matter? Compressing a gas reduces its volume and the ways its particles can spread out. That lowers entropy, which in turn raises the free energy of a gas at higher pressure. Here is a quick rule for Q. Include gases with their partial pressures. Ignore pure liquids and solids. Build Q so it is unitless by dividing by the standard state, which is 1 atmosphere for gases. Let's calculate delta G for making ammonia. Say nitrogen is at 10 atmospheres, hydrogen at 30, and ammonia at 1. Build Q as the pressure of ammonia squared over the pressure of nitrogen times the pressure of hydrogen cubed. Plug Q into delta G equals delta G naught plus RT times natural log of Q using R equals 8.314 joules per mole Kelvin and T equals 298 Kelvin. Because Q is far less than 1, natural log of Q is negative, so RT times natural log of Q lowers delta G below its standard value. The reaction is more spontaneous under these pressures than at 1 atmosphere. It is time to reveal the answer for our pop quiz. The correct choice is right to ammonia. Increasing pressure favors the side with fewer gas particles. Here, products have 2 moles of gas while reactants have 4. Raising pressure makes Q smaller and delta G more negative, pushing the reaction forward. Here are some common pitfalls. First, when you see natural log, use the 8.314 joule constant, not the gas constant in liter atmospheres. Second, do not put liquids or solids in Q. Third, always build Q so it is unitless. So far, we have the pressure link, how to build Q from gas pressures, and why delta G equals delta G naught plus RT times natural log of Q can make a reaction more or less spontaneous. Curious how much you're remembering? Your personalized practice test, flashcard set, and study guide are all waiting for you. Just tap the link now and keep watching. Future you will thank you. Try a different pattern. For hydrogen and oxygen making liquid water, liquids do not appear in Q, so Q equals 1 over the pressure of hydrogen squared times the pressure of oxygen. Increasing the gas pressures makes Q smaller, which again makes delta G more negative. Here's a subtle point. If the number of gas moles is the same on both sides, and you compress the mixture uniformly without changing the mole fractions, Q stays the same. That means the pressure change alone won't affect spontaneity. The composition can still shift, but uniform compression by itself doesn't. Let's practice the workflow. First, write Q with gases only. Second, set R equals 8.314 and pick the temperature in Kelvin. Third, compute RT times natural log of Q. And lastly, add it to delta G naught from a table to get delta G at your conditions. One last unit reminder. The 8.314 joule constant pairs with natural logs and energy-based calculations. The 0.082 liter atmosphere version is used for pressure volume work and doesn't fit into the natural log expression for delta G. To recap, Delta G equals delta G naught plus RT times natural log of Q, the equation that links pressure to spontaneity. Build Q using gas pressures only. Use the 8.314 joule constant and remember, higher pressure favors the side with fewer gas moles. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.